We're now going to introduce parallel circuits. So something is considered a parallel circuit whenever the current has a choice to go through one object or one resistor or another. Let's begin by going over the rules for parallel circuits. First rule is for voltage. Voltage in a parallel circuit is constant. Which means that the total voltage is equal to the voltage in resistor 1, equal to the voltage in resistor 2, and so on, for however many resistors we have in our parallel circuit. The second rule for parallel circuit is that current adds. So the current total for a parallel circuit is equal to the current in resistor 1 plus the current in resistor 2, and so on for however many resistors we have in parallel with one another. And the last quantity is resistance, and this is a little bit unique, and this is reciprocals add. So what that means is that 1 over R total equals 1 over R1 plus 1 over R2, and so on for however many resistors that are in parallel. And again, I would refer you to our mnemonic device, Veer, Saka, Pakara. So these are the rules that you will need to know to analyze resistor circuits. So we're now looking at parallel, voltage is constant, current adds, resistance reciprocals add. We can now go ahead and take a look at our first circuit. I encourage you to review the steps that I've outlined. I'll be talking through them, but they're always there for you to refer to as you're doing problems. So let's take a look at parallel resistor example 1. So remember the symbols. This is our power supply, and it is in fact 12 volts. The longer end is the positive, the shorter end is the negative. Resistor 1 is 15 ohms, and resistor 2 is 10 ohms. So why is this a parallel circuit? Well, here is why. So the current comes out of the power supply. Everything's fine. Coming along, and we get to this point here. What do we have? A choice. You can go through resistor 1, or you can go through resistor 2. Because you have that choice, this is considered a parallel circuit. So, just to clarify, it has nothing to do with the fact that resistor 1 and resistor 2 are geometrically parallel, which of course they are the way this circuit is drawn. That is not what it means. It means you have choice. In this case, the current can pick, does it go through resistor 1 or does it go through resistor 2? And in fact, it will split. So in this case, because this is 15 ohms in R1 and 10 ohms in R2, I would expect more current to choose to go through R2 because it has less resistance and it should be easier to go through. And I would expect less current to pass through R1 because it has a greater resistance and so it is harder to go through. So let us find the total resistance because that is the first step in any circuit. So what we're going to do is we're going to apply the rule for resistance in parallel. So the rule for resistance in parallel was reciprocals add. So let's write that down. So 1 over R total is equal to 1 over 15 plus 1 over 10. Now, you're adding fractions, so of course you realize you're going to need a common denominator. Common denominator of 15 and 10 is 30. So 115 as a fraction over 30 is going to be 2/30. 1/10 as a fraction over 30 is going to be 3/30. Okay, so we add across the top. 2 plus 3 is 5 30ths. So I know that 1 over our total is equal to 5 over 30, which reduces to 1 over 6. So that means that if I flip 1 over our total and I flip 1 over 6, I get my total resistance in this parallel circuit is equal to 6 ohms. Now there is a shortcut for doing all the work with fractions, which is going to come in handy, especially if you have more than 2 resistors in parallel. So the way that you're going to do that is you're going to use the x to the negative 1 button in your calculator. And you're going to see that button just above the x squared. And so what you would do in this case to figure out your total resistance is you would do the following. You would type into your calculator 15, you'd hit that button, and negative 1 would appear. You'd hit the plus button, you'd hit 10 because our second resistor is 10 ohms. You'd hit the negative 1 button, and you would press enter, and it would give you a number. And your calculator is going to give you something like 0.16667. Really, it looks like 6 repeating. And that's fine because you're really not going to do anything with that number. You're immediately going to hit the x to the negative 1 button one more time. So you're going to, and when you do that, your calculator screen is going to read 0.16667. You hit the negative 1 button, it appears. And then you would press enter, and it's going to tell you 6 ohms. And you can see that's exactly the same total resistance that we got when we did it by hand using fractions. This is a much faster and probably more reliable method in that you are less likely to make a mistake finding the common denominator. So I would highly recommend that you do it this way. It is important that you understand, of course, the process, but in terms of actually solving problems, I think the x to the negative 1 button is a very valuable way for you to know how to approach this. So let's go through and continue to analyze the circuit in exactly the same way that we did before. So just like in a series circuit, in a parallel circuit, the first step is to find the total resistance. And you've done that. It is 6 ohms. Once I know my total resistance, in this case total voltage was given, I could go ahead and find my total current. So I have 12 divided by 6. My total current is going to be 2 amps. Now you have to go back to your rules here because what's going to happen is all 2 amps are going to come out of the power supply. All 2 amps are going to go into this junction, right? We call it a junction because there's current going in and current going out. So the current going in would have 1, essentially we all be together, and then it would split coming out of the junction depending on whether it would go through R1 or R2. And what happens here is that current is not going to be constant like it was in series. So if we go back to our rules at the top of the page here, so let's glance up. In a parallel circuit, voltage is actually constant. So what that means is whether or not the current goes through R1 or R2, all 12 amps are going to be used getting through that resistor. So I can use 12 volts here across resistor 1, or I could use 12 volts here across resistor 2. And so what I'm going to do is I'm going to plug those 12 volts into the chart, the VERP table at the bottom. So I'm going to put the 12 volts here and 12 volts here. Recall, the VERP table is laid out so that V equals I times R, and the power is equal to current times voltage. So we have to go ahead and figure out the current. Well, if I know voltage and I know resistance, I should be able to divide them. So 12 divided by 15 gives you 0.8 amps, and 12 divided by 10 gives you 1.2 amps. If we refer to the rules for a parallel circuit for current, it says that it adds. So if I do 0.8 plus 1.2, I get 2 amps. So just to recap, parallel circuit, voltage is constant, current adds, and the way that we got this 6 ohms was using the rule reciprocals add. We're now going to do the power check, and that works exactly the same way that it did before. So to find our power, we're going to take our 12 volts, and we're going to multiply by our 0.8 amps. And we are going to get 9.6 watts. Now you may have to keep 2 decimal places, especially depending on the fractions. In this case, it was just 9.6, but in future problems, you may have to round and keep 2 decimal places in order for the power check to actually come close and work. And so 12 times 1.2 is going to be 14.4. And so what we're going to do is we're going to add 14.4 plus 9.6 to figure out our total power. And we get 24 watts. 24 watts. So now, again, we're going to perform the power check. So the power check simply says that power total is equal to I total times V total. So we'll just use our chart here. Our I total was the 2 amps. Our voltage total was the 12 volts. And when we multiply them, we get the 24 watts. So you can see that when we added down the column, and when we multiplied, we got the same thing. So we have a successful power check, indicating that we have likely analyzed this circuit correctly. So that is your first parallel circuit. And again, take a look at it. What was the key? What was the key difference? Choice. The current does not just have one path. It has a choice. And that is what makes it parallel. Let's take a look at the next problem. So in this case, we have 3 resistors in parallel. So we'll go ahead and just label the information off the chart, just like we've been doing in the other problems. So we know our power supply is 60 volts total. That's the positive and negative end. We have 8 ohms, we have 12 ohms, and we have 24 ohms. So the way that we're going to get our R total is using the inverse button, which was the shortcut that I showed you in the last video. So you're simply going to type 8, hit that x to the negative 1 button, and you'll see 8 to the negative 1 appear, plus 12, hit the x to the negative 1 button, and that will appear, plus 24, hit the x to the negative 1 button, and then you're going to press enter. It's going to give you 0.25. You're not going to type anything. You're simply going to hit X to the -1 button, and automatically on your home screen, you will see 0.25 to the -1 appear. And you're going to press enter. And you'll see that that means that this circuit has a total resistance of 4 ohms. This is a pretty quick way to find the total resistance in a parallel circuit. So let's go ahead and fill out the chart here. We have 4 ohms is the resistance of this circuit. And just like before, you could find your total current. So we know 60 divided by 4 is going to be 15 amps, which would be a phenomenal amount of current. So that means that 15 amps comes out of our power supply, and then it has a choice. Some of it will go down through R1, some of it will go through R2, some of it will go through R3. And then, of course, it all comes back into the negative side of the power supply, which could be a battery or any other direct current source. So, if we go to our rules for a parallel circuit, voltage is constant. So even though the current's going to split, it has to use all 60 volts no matter which path it takes. So for the current going through R1, it will use 60 volts. The current through R2 will use 60 volts, and the current through R3 will use 60 volts to get through that particular resistor. And so I'm going to go ahead and fill out my voltage column in the verb table. And now we're going to go ahead and remember the layout of the chart, V equals I times R. So if we know voltage and we know resistance, we could calculate the current through each branch of this circuit. So let's go ahead and do that. So 60 divided by 8 is going to be 7.5 amps. 60 divided by 12 is going to be 5 amps. And 60 divided by 24 is going to be 2.5 amps. So we've now found all of the current in this circuit. So the last thing to do is to complete the power check, which is always going to be power is equal to current times voltage. So we'll find the power through each resistor by multiplying. So 7.5 times 60 is going to be 450. 5 times 60 is going to be 300. And 2.5 times 60 is going to be 150. And so when we add those, 150 plus 300 plus 450, we get 900. So let's complete our power check. So my current total was 15 amps. And let's clean that up. 15 amps times 60 volts. So if I multiply 15 times 60, I get 900. So you can see that when we added down our columns and when we multiplied the totals, we ended up with 900. So our power check does in fact check, indicating that we have correctly analyzed this circuit. So there's one more parallel circuit practice problem that you should go ahead and try on your own to make sure that you are comfortable with parallel circuits. And remember, they're parallel because there is choice. It has nothing to do with the fact that the resistors are geometrically parallel. It is the fact that the current has a choice of different paths. So make sure you know your rules, vir Sakapakara, and if you feel comfortable with both series and parallel circuits, we should be in good shape to move on.